So I'm going to start with problem 69 rather. Okay, so I'm just reading off the book. So there is a feedback amplifier there. So this is 1169, and they have a common gate amplifier. This is the picture that they have. So this is a common gate here, and there is a bias network that is not shown, and there is a current input, okay, that comes into here. So the input is a current, and then this is the output over here. It's a voltage, and then there is a capacitive divider network over here, and there is a feedback with a common source amplifier. So this is common source over here. So this is a trans resistance amplifier. So we have eventual feedback gain is going to be VO over IS. And you can see that this is your feedback coupling point here. And you're coupling the output is being sampled through this capacitive network over here. So the beta network is going to be the two capacitors and the common source amplifier. Okay, and then this part over here is your A. So this is the beta here and the A over here. And they want to, so they want us to find AF, and I remember I said that the common well, I already show AF over here. They want us to find that, and they also want us to find the input impedance, even though we may refer to it as R of I usually use the more general term input impedance, but if it's not frequency dependent, then it's just a resistance. That's just the difference. And they also want us to find the output impedance. So the output impedance would be looking into the output, and the input resistance would be looking into the input node there. Okay. They tell us that the capacitors are sufficiently small, so they really don't load the output in terms of whatever load. So you can have a load impedance over here. So this capacitor don't load the output in terms of that eventual load impedance. And we can neglect the output resistance of the transistors. So in that case, the transistors are going to be modeled as just a purely voltage dependent current sources, okay, and with a GM. And they want us to find these quantities for, this is QF and this is Q1. So they give us some GM values. So GM1 is 5 milliamps per volt. GMF is 2 milliamps per volt. We have values for the capacitors of 0.9 and 0.1 picofarads, C1 and C2 respectively. And the RD is, the values of RD given is 10 kilo ohms. Okay. So, let's see. So what I meant by neglecting at all is that transistor models, they get more complex depending on the need and the analysis that you're doing. The simplest model of a Mosfet is this voltage dependent current source, where this is your GM times VGS. So this is the source, this is the drain, and this is the gate, and this is your VGS. So that's the simplest one, and that's what we're going to be using. The next up is when you have an output resistance for the transistor, and we're saying that we're going to neglect that, so it's high enough that we can say it's not there. Okay, but imagine, as you are doing more and more things, you need to make this this model more complex. You can add a gate capacitance, you can add a gate to drain capacitance, and if you're doing microwave stuff, you can start adding inductors and all kinds of things, right? So, but for us, it's going to be just that GM. Okay, that's what is meant there. So the first thing that we want to do is to realize that we already have biased the amplifier to operate in the linear region, and we're talking about a linear amplifier. So we're going to be looking at the small signal behavior of it. And if we do that, we realize that the biasing as well as the power supply are signal grounds. This is the A circuit here as presented for a small signal. And then this is the bias, which is really a signal ground. And here we have a signal ground. That's what the power supply was. Okay? And we want to, just for the A circuit, we wanted to see what was this RI. How did we get that? If you look into that terminal, for a Mosfet, looking into the source, the input resistance is 1 over GM. In this case, is GM1 because that is Q1. Okay, and we were given that GM was 0.2 or 1. I'm sorry. It was 5. GM was 5. So this is 1 over 5.2, and it was 5 milliamps per volt. So 0.2 in that case, we're going to get kilo ohms here. Okay. So when you're working with voltage in milliamps, then the resistance is in kilo ohms. You can also look at what is the A from input here to output. So this is input to output. What is the A? And then that would be which that gain is actually given by RD, which we, they gave it to us. That's 10 kilo ohms. And then if you want to find the RO at this point, just for the A part, looking into that node, which is the output, if you want to find the RO looking into that output, what you see is that RO is RD. Okay? Because remember what is in here. What is in here inside the transistor, the model is a current source which has infinite impedance. So from a small signal perspective, that RD shows up in parallel with that infinite impedance, so all you see is RD. And they also gave us that was 10 kilo ohms. Okay. So that's on the A side, just for more insight and clarity. We can do something similar for the beta part. So remember that the beta part was the common source here, and we were getting, remember that the output was over here somewhere, and we were sampling it through a capacitor divider. So here's the output, which we're going to model as a voltage source, and we had a current which was a feedback current. So this is the junction point, and we're coupling that current with the input current as a summing junction. So the current here is the feedback signal. So that's your feedback signal, because this is your beta network. So the beta is defined as the output IF divided by what you are sampling, which is VO. And if we look at the equation for a capacitor divider, this was C1 and C2. So for a capacitor divider, what we're going to get is C1 over C1 plus C2, and that is going to divide the effective GM that we see in the feedback network, which is GM for the feedback transistor. So this is QF. And you can go through the arithmetic, and you are going to get that beta is 1.8 milliamps per volts. So beta, this amplifier, the beta network, is a transconductance amplifier. Okay? So, so what other things we can do? We can also calculate with those numbers. We can calculate an AF. Which in this case is going to be A. Well, it's always A plus divided by 1 plus A beta. And if you go with using the numbers that they gave us, you get you get 0.53 kilo ohms. And with the add in and add out that we calculated before, remember that the closed loop is always the open loop divided by the feedback factor. And for adding with those numbers, we get 10.5 kilo ohms rather. And the closed loop add out is the open loop divided by the feedback factor. And we get 526. So so I wanted to do this one because it's probably the most complex thing that I could throw at you. Let's take a look at it. 1182. So 1182 says that an op amp having a low frequency gain of 100,000 and a single pole roll off at 1,000 radians per second is connected in a negative feedback loop via a feedback network having a transmission K and a two-pole roll off at 1,000 radians per second. Find the value of K above which the closed loop amplifier becomes unstable. Okay, so let's take a look at that. So we are given the values of the open loop gain, but the beta is given in terms of this transmission. So what we can write, so this is 82. What we can write is that AS beta S, so in terms of the frequency dependent loop gain, is equal to 10 to the 5th K divided by 1 plus S times 10 to the 3rd, and all that is going to be cubed because we have 3 poles. We have the pole of the A network and we have 2 poles in the beta network. We're told that. So that's why we have 3 poles here. Okay? Alright, so then this is just a matter of some algebra of substituting S for J omega. So now my expression looks like this. okay? And then taking first the magnitude. So now this is a complex expression, so I have to take the magnitude of that. Let's use some algebra there. So we have that the magnitude of a j omega beta j omega is going to be 10 to the 5k divided by 1 plus omega square. If you do the algebra, this is what you get, okay? Divided by 10 to the 6 to the 1.5 power, okay? That's just taking the algebraic magnitude. And then I also need to look at the expression for the phase. And as a function of omega, and where you get, if you do the algebra, you get -3 tangent inverse of omega divided by 10 to the third, okay? So what you want to know is what is the frequency first the value of k about which the closed loop amplifier becomes unstable. So the first thing that you need to do is find the omega 180. Okay, what is the omega when this becomes 180 here? So you can plug it in the magnitude here and solve for k. This is an important technique. It's always going to be, when looking for stability, it's always going to be the same. You come up with the magnitude expression, the phase expression, find the 180 omega or frequency, and use that to find some other parameter in the magnitude expression. So to do that, I write minus 180 here is equal to -3 tan inverse of omega 180 divided by 10 to the third. And if you solve for that, then you get that omega 180 is equal to 1732 radians per second. Okay, and then you use that in the magnitude expression. So that would be, if you solve for, if you plug the omega 180 in the magnitude expression, you will get that the following expression here. So that's a square there. Which is equal to 0.125 times 10 to the 5th k. So you get that expression. for the magnitude, and then let's just write this for a stable operation. We want at that frequency the magnitude of the loop gain to be less than 1. So if we use that, then we have has to be less than 1, which means that K has to be less than 8. Okay? So that answers the question of find the value of K above which the closed loop amplifier becomes stable. So if K is above 8 times 10 to the minus fifth, then the amplifier will become stable. And that was problem 1182. Any questions about 1182?
Yes, sir. Quick question. Just in reference to the graph, the phase and frequency graph with K, like for stability, would K be on to the right or the left of the y-axis, the Jy or J omega axis?
No, don't confuse K with the poles. K is just a gain.
Oh, okay, got
K is just the gain of the beta network in this case.
Got it. All right, thank you.
Which, as you can see, the beta network tends to have a very low gain. Okay, that's typical. Did that help?
Yes, it did. Thank you.
Any other questions about 82? All right. Now let's do 83. So 83 says, consider a feedback amplifier for which the open loop gain AS is given by, and they give you the following expression. So this is 1183, and they give us this expression for A, and this is going to have 3 poles. And there is another couple of poles over here. Let's see. Looks like a 5 there. That's a 2, so double pole, and this is 10 to the 4th. So it says consider a feedback amplifier for which the open loop gain A of S is given by that expression. And then it says if the feedback factor beta is independent of frequency, find the frequency at which the phase shift is 180 degrees, and find the critical value of beta at which oscillation will commence. Okay? So again, this is very similar to the one before, but these problems are important. We're going to again write A of J omega, and that's going to be This is 10 to the 4th over here. And we're going to find the expression for the phase. So for the phase, the expression is going to be here 10 to the 5th, and that is the expression for the phase. Then they were asking us about what is the oscillations well, the first question is, when is the 180-degree phase shift going to happen? So all I have to do is to equate this expression to 180 and find the omega 180. So I can write
that -2 just came from the exponent, right?
I'm sorry?
The -2, that just came from the exponent, correct?
Yeah, so that's taking the doing the algebra for the phase expression out of A of j omega. If you take that expression, you have to separate it into the real and the imaginary part, and then essentially take the ratio of the imaginary part to the ratio of the real part, and if you do some algebra and some trig identities, you get that.
Okay, thank you.
Yeah. So so here we have 180 minus tan inverse of omega 180 over 10 to the 4 minus 2 tan 80 tan inverse okay. So whenever you get something, so now you have to solve for omega 180, okay? And this is this is what is called a transcendental equation. So it doesn't have a analytical solution. So essentially what that means that you have to do by trial and error, or that's the fancy name for trial and error is numerical methods, okay? So if you do that and solve that transcendental equation, you get that omega 180 is 1 times 0.95 times 10 to the 5th radians per second. Okay, so that's the frequency. So now you want to know what is the magnitude of A at that frequency. So again, you go back to A of j omega and find the magnitude. So square root of the real square plus the imaginary square, and you find that A at that frequency, the A is 10.95 square times 1 plus 10.95 square, and that is dividing 10 to the 4th. which is equal to 413.6. Okay. Then we have the omega 180. We have the gain, the magnitude of the gain A at that frequency. So we can say that for a stable operation, the magnitude of A times the beta at which oscillations are going to commence. We're going to use the subscript CR for critical. So it'll be the critical frequency of the circuit. Has to be less than 1. That's the boundary. Okay? So then beta is just or beta has to be less than 1 over the magnitude of A, which is turns out to be 4.2 times 10 to the minus 3. So what that means is that we get oscillation at beta equal to 2.42 times 10 to the minus 3, and if beta is greater than that critical beta, then that implies unstability. Okay, so those are the examples that I wanted to work today. Any question about this one, the 83?
When we were calculating the magnitude of A, why wasn't 1 plus 10.95 squared inside the square root?
It was. We had 1 inside the square root and 1 outside the square root. Remember that we had this this factors. There are 3 poles in the expression. Okay, so you actually have to do the algebra, and which is sometimes the algebra tends to be the most tedious and just painful part of this. But if you do the algebra and substitute for the omega 180, you get the expression, that expression for the magnitude of A. But you have to separate the real, you have to separate the real and the imaginary part. So you would have to go back to the original J omega expression. Essentially take the complex quantity you get of the denominator and just work out all the steps of the algebra, which are, I'm not saying they are not numerous, they are, but you will get to that expression. Okay, there is a lot of algebra in getting. There is a lot of algebra in getting from this type of expression to which essentially won't have a J. It'll be a real quantity. But to go from here to there, that usually that's a lot of algebra. Okay, and to a lesser extent, to get from here to the face, there is also a little bit of algebra involved. But you know, you have to separate essentially this here, okay, is going to be the square root of the real part of A of j omega square plus the imaginary part of A of j omega square. And to be able to separate the imaginary and the real part, you have to do quite a bit of algebra on that. Okay? Did that help?
Yeah, it did.
So if you find yourself doing a lot of algebra, to do that, don't be surprised. It is what it takes. Okay?